Welcome to another episode of Organic Chemistry series. In the previous video, we basically discussed about the different arrangements and conformations for two really basic but important molecules. Can you remember them? One of them was CH3, which is going to be ethane. And the other one was simply just one more carbon connected to this chain, which makes it CH3, CH2, and CH3, which is going to be propane. So we discussed the different arrangements of these two molecules in the previous video in details. Now, today we want to make this topic a little more extended by analyzing another molecule which has a longer chain. In the previous video, we talked about propane with 3 carbons in its main chain, and today we are going to analyze the butane molecule. But before starting the whole process, don't forget to like this video if you find it useful, subscribe to our channel, and wait for our next content. Now, to have a short review, I have 2 images or 2 conformations here for you. The one in the left, when you look at this, you can see that the 2 hydrogens that are connected to 2 different carbon atoms are face to face. It means when you look at them, they don't have a difference between themselves. They don't have an angle. Their angle is 0. Okay, but if you rotate this shape by 60 degrees, if you rotate just one of the carbons by 60 degrees, we can have another conformation, which is going to be the right one. In this one, the hydrogen connected to one carbon is located between the 2 other hydrogens which are connected to the other carbon. And we primarily know that this conformation, the conformation on the right, has less steric hindrance. And because of this less steric hindrance, it is more stable and it has less potential energy. However, the one that exists on the left has more steric hindrance, and because of more steric hindrance, it has more potential energy and it's more unstable. And we also had 2 names to making referring these 2 molecules a little easier. If you can remember, the left one was, yes, perhaps, it was eclipsed conformation, and the right one was staggered conformation. That's great. I guess we had an acceptable review by now. Now let's head to the next molecule. Okay, now we said that we want to analyze the butane molecule. But first, before starting this process, we have to know the formula. The chemical formula of butane is C4H10. So 4 carbons connected to 10 different hydrogens. Great. But from this chemical formula, we do not get a really clear understanding about which part are we going to analyze about the conformations. I'm going to extend this to another form. I show it with 2 central carbons that are connected to each other, and one other carbon here, and the other lines that I draw are showing the number of hydrogens that are connected. Great. The carbon-carbon bond that we are going to discuss and we are going to elaborate on this video is basically this one. When we look at this molecule from this angle, we can see that 2 carbons are connected to each other, and to each carbon there is one methyl group connected and two different hydrogens. You can see this easier in this shape or in this figure. So this dot is showing the carbon in front, and this circle is showing the carbon in back. So if we take a deeper look, we can understand that this methyl group is connected to the front carbon. However, this methyl group is connected to the back carbon. Great. Now, when we were talking about the molecules like ethane or the molecules like propane, we basically had one eclipsed conformation and one, yes, you're right, and one staggered conformation. But what is the conformation like here? In this molecule, the number of conformations are different. Starting by taking a look at this one, we can understand that the two different methyl groups has the less steric hindrance possible, and because of this, the potential energy of this molecule is going to be minimized. This minimized steric hindrance is because that two different methyl groups are located in the the most distant areas possible. And because they're too far, they don't have any noticeable, let's say, steric hindrance. But let's try to rotate one of these central carbons. When I say central carbons, I'm basically referring to this one and this one. If we try to rotate one of these carbons by 60 degrees, we are going to have another conformation like this. Now, I'm going to ask you, which of these two conformations has, let's say, more steric hindrance? Yes, you're right. We can say that the right one has more steric hindrance because one methyl group and one hydrogen, again, one methyl group and one hydrogen, are somehow face to face. And because of this conformation, because of this arrangement, the methyl group and the hydrogen has steric hindrance. And totally, we can say that the steric hindrance of the conformation on the right is more than the conformation on the left. So the conformation on the right is not as stable as the conformation on the left. Great. Now let's try to rotate this molecule another 60 degrees. Now look here. If we try to rotate it one more time, we can see that two methyl groups are getting closer. That's fine. We can even rotate this one more time, which is going to be like this. Now, take a really careful look at this conformation. In this conformation, which we may call the eclipse conformation, just for now, we're going to have a different name for this, let's say, in the following steps. Two methyl groups are exactly face to face, and they can cause a great amount of steric hindrance. Because of this great amount of steric hindrance, this molecule is somehow unstable, and you cannot easily find this conformation of butane in a sample. Great. We can even rotate this molecule one more time by 60 degrees, which can cause this conformation. And the process can be continued easily. Just let's say rotating the carbons 60 degrees, another 60 degrees, and to see what kinds of conformations are going to be formed. But the key point is that we have to define that which conformation has the most stable let's say, form, and which one is the least stable form. On the other hand, we have to define the potential energy diagram. So to be a little more accurate, I'm going to provide you with the diagram here. Great. Now, let's take a look at this diagram. Before we start to analyze this diagram, we can say something really easily. Now, look at the conformations that exist or are located in the lower part of the diagram. You can see that none of the groups, when I say group, I mean the hydrogen or the methyl group, none of them are face to face. I mean, considering our prior knowledge about the conformations, we can say somehow they are staggered conformations. But let's take a look at the conformations that are located on the top of this diagram. All of them have some groups that are face to face. I mean, for example, in this one, hydrogen and methyl groups are face to face. Two methyl groups are face to face, and hydrogens as well. And this one is exactly the similar as this one. So they exist on the top of the diagram, but this group, they exist in the lower part of the diagram. That's because when two groups, like methyl group, like hydrogen, like any other possible group that can be connected to the carbon, when they are face to face, they can cause a really noticeable amount of steric hindrance, like this, like this, like this, and this one. Because they can cause a noticeable great, let's say, amount of steric hindrance, they are basically less stable and they have more potential energy. So when you look at this diagram, the peak areas of this diagram, the peak areas actually belong to the conformations that are eclipsed. That's fine. The reverse can be also concluded, and the conformations that are staggered, they don't have face-to-face groups, has less, let's say, steric hindrance, and they are more stable. But let's be more accurate. When we look at this area, we can understand that this one has the most potential energy and is the least stable. You may ask why. I have to say that methyl group is a larger group when it's compared to hydrogen, and because two larger groups are face to face, they can cause more steric hindrance when they are compared to this or this conformation. So if you look at these numbers, you can see that there is a little difference between those two conformations. This one has 3.6 kilocalories compared to the most stable conformation, but this one has 4.9 kilocalories compared to the most stable conformation. So let's go to the other conformations that exist here on the lower parts. Starting with these two conformations. When you look at these, you can see that two methyl groups are not face to face, but there is a 60-degree angle between them, and it can be the result. So the methyl groups can cause a little steric hindrance as well. It's not as much as the steric hindrance that happen in the, let's say, eclipsed forms or eclipsed conformations, but it is important. And because of this, you can see that the energy level of these two conformations are a little more than the other conformations. Now, let's make it easier to refer. When two methyl groups or when two largest groups or as far as possible, we can call them the anti-conformation. In anti-conformation, the degree, I mean the angle between the between the two largest groups is about, or exactly, 180 degrees. And here you can see it as well, 180 degrees. However, in the two other conformations, you can see a 60-degree angle between the methyl groups. So to make it easier, these two conformations are called gauge conformations, and these two are called anti-conformations. So because of the possible steric hindrance between the two methyl groups in the gauge conformation, it is a little less stable compared to the anti, and it has 0.9 kilocalories per mole of potential energy, let's say, compared to the anti. So this is going to be the diagram of butane molecule, I mean the diagram of conformational analysis. We can easily make this make this topic more extensive, because if we add any other groups, I mean methyl groups, ethyl groups, or even more number of carbons, this diagram gets more complicated, and different shapes and different conformations with different potential energy levels are going to be generated. Now, I think that's enough for now. For the next time, we are going to wrap this up, do a really important, let's say, solve a really important example together, and head to the next subject. Thank you so much for watching this video. If you found this useful, try to share it with your friends and hit that like button for us. This is Chem Explain.